We spend a good amount of time doing these natural transmutations where we break one element down to another by releasing alpha, beta, or positrons. But if you don't feel you need to do this, no need to actually watch the slide. You can fast forward a little bit. I'm just going to quick fill this in. Remember, if you need to know how these things go, you've got table N that shows how different elements break down, releasing what kinds of particles. You also have table O on the next page at the top that shows you what these things look like. So first thing we have here is the alpha particle. We have plutonium breaking down by releasing the alpha particle. So I'm going to subtract the 4 from the 239. That gives me a mass of 235. And then I subtract 2 from 94. That gives me an atomic number of 92. And when I look at my reference table, it tells me that element 92 is uranium with a U. K19, if we look that up, it releases a beta particle, so that's an E with little -1 as its atomic number and 0 as the mass. The mass did not change because the thing we released has no mass, so the mass of the other piece stays as 42 as in the original nucleus. The atomic number is -1, so we have to say what goes with -1 to give us 19 that the case started as, and that's going to be a 20 right here. So 20 and -1 add up to the 19 over there, and that is going to be element Ca. It's calcium 42. Down here at the bottom, this thing right here is a positron. That's the E with the +1. So I'm going to just look at these numbers. We had 10 on the bottom on the left. We have to find some number over here that now goes with 1 to equal 10. So that's going to be 9. That tells us that element number 9 is fluorine. And now we just have to look at the masses. Neon started as 19. This part we lost has 0. So that means the mass up top here is going to stay as 19. Let's start by filling in some blanks and finding some missing pieces. So on the left side of this arrow in the first equation, we have a carbon and 4 different hydrogens. And when they get added together, what's it going to look like? Well, we're just going to have carbon with 4 hydrogens. So nothing tricky. Just put them together, we have CH4. On the bottom one now, we have a missing piece because we start with CH4 and we break it apart into multiple pieces like we've seen so far with nuclear chemistry. If one of the pieces that it breaks up into is CH2, well, what's going to be left over? From this thing right here, this piece that we're left with, we know we used up the carbon and we used up 2 of the hydrogens. So what's left? All we have is 2 additional hydrogens. So all that's going to be left right here is going to be H2. And we've done that a little bit in the last couple of days. Now we're going to see how this works today. Because some quick definitional stuff that we've seen a little bit already, but to remind you, in chemical reactions that we've seen pretty much the rest of the year, the pieces are staying the same, it's just they're moving around. So you have the same elements becoming different arrangements of the same elements, just like in either of these reactions here. Nothing's changing. In nuclear reactions, it's different because you're actually forming a new element. That's this word transmutation, and that's the title of what we're doing today. We're going to look at different types of these reactions, exactly how one element can turn to a different element. So we looked a little bit the last couple of days at alpha and beta particles and positrons, how these pieces can get kicked off to form new elements naturally. Today we'll look at how this maybe doesn't happen always naturally, how we can actually make some element turn into a different element artificially. A transmutation whereby one element turns into a different element can happen in one of 2 ways. It's either a natural or artificial event. In a natural transmutation, it's a spontaneous process where something that has a strange neutron to proton ratio makes it unstable. So it kicks off either an alpha particle, a beta particle, or a positron, as we've seen, some kind of smaller piece like this, and then the leftover stuff is some other element like this. So uranium would kick off this small alpha particle, and what's left over, the thorium, is pretty much close to what we started with. It's a little bit smaller, and hopefully it would be stable. Otherwise, it may continue to decay a little bit more. An artificial decay, an artificial transmutation, is not a spontaneous process. This would normally not happen on its own. You start with 2 reactants. So in the first thing, in natural, where you only have 1 reactant that breaks down on its own, in artificial transmutation, you need 2 reactants. You need this otherwise stable nucleus that's not going to break down on its own, except we launch this thing, this little fast-moving particle at it. So we launch either a neutron, a proton, or some alpha particle, something like that, at the target nucleus, and that causes it to explode, essentially. It causes it to become unstable and then break into multiple pieces or do whatever it's going to do. But it wouldn't happen on its own, except that we decide to hit this thing with the smaller piece and actually fire it at this nucleus here. We've talked about natural for a couple of days, so we're going to focus now on artificial transmutation types. This can either happen with a neutron being launched at the target nucleus. So it's just an uncharged particle. Again, this target nucleus is stable on its own until we actually shoot a neutron at it. We speed it up in a particle accelerator and launch it at this target nucleus, which makes it break pretty evenly. And the natural transmutation, you'll see a small piece like the beta particle or the alpha particle break off, and what you're left with as the other element is pretty large compared to what you started with. It's most of the original size of the unstable element. In this case here, the neutron hits the target nucleus and it breaks into these two pretty evenly sized pieces here. They're both pretty large compared to what you started with already. It's not that a small piece breaks down. You're left with two chunks of pretty large elements or whatever's left over. In the other case, instead of a neutron being launched, you launch some kind of charged particle. So either a proton or an alpha particle with a positive charge, and this is what you're launching at the target nucleus. In this case, it has to be sent very, very fast because it needs to overcome the repulsive forces from the nucleus. If you're launching a positively charged particle at a positively charged nucleus, they're going to push away from each other. So you have to make sure you're not hitting them at any strange angle like this, and they have to be moving very, very fast to, again, overcome those forces trying to push them away from each other. So I mentioned this a little bit in an earlier slide, but important to go over it again. How to tell the difference between natural and artificial transmutations, natural and artificial changes. A natural transmutation, when one element turns into something else, is like this one here. It's like what we've seen already the last couple of days. It's one reactant, so only one thing on the left, because it's breaking down on its own. It doesn't need any outside help. It's unstable based on this proton to neutron ratio, and it'll break down by kicking off this thing right here, either an alpha particle or a beta or a positron, and then whatever is left over is the rest of the pieces. So in this case, it's going to kick off a small thing, the alpha particle. It took 2 protons and then 2 more neutrons, so a total of 4 mass units, and just you subtract those things from your original numbers over here to get whatever you're left with after the fact. Just notice how the piece that kind of remains after the whole reaction takes place, this lead-204, it's not that much smaller than your starting material. So natural transmutations, you're kicking off small pieces at a time and not getting much smaller. You may have to do a couple of these little reactions in order to get something stable, but it's small steps, not something major. Artificial transmutations are different because you have, the easiest thing to see are 2 reactants. There's always 2 things on the left. You're shooting this neutron at this cobalt. It's not going to break down on its own. So it's not just like up here, one element by itself that's going to naturally break down. You have to either launch a neutron like right here, or one of these alpha particles, or a proton. You're shooting and launching and propelling some smaller particle at this otherwise stable nucleus in order to get it to be unstable by turning it into this guy right over here. So this is really even an incomplete equation. You'd also have something else going on here going forward, where this now unstable nucleus on the right would break down further into something else. So usually into multiple pieces, but artificial is important. You have 2 pieces on the left, and that's the easy thing to recognize. It's not just one thing by itself. So always look for 2 pieces on the left, and that's going to be your best indication that it's not something that's happening naturally. We are making this happen by hitting these things together. One type of artificial transmutation is called fission reaction, or nuclear fission. And if you've ever seen that word somewhere else in your life, it means to split something. So the particle fired at the target nucleus makes the target nucleus become unstable and split in half, essentially. So that's like I was saying before. You get not these 2 little particles breaking off, but the pieces you're left with are pretty big. So you see the krypton here with a mass of 90, barium with a mass of 143. These are much, much, much larger than the little alpha particles or beta particles in the natural transmutations. So the pretty massive uranium breaks down to 2 still pretty substantial pieces after that. Additionally, it releases a bunch of these neutrons that'll go on and do other things. These reactions are really crazy, many times more powerful than regular chemical reactions. See here, about 1 million times more energy gets released. That's why we have nuclear power plants, because they release a lot of energy for pretty small reactions going on compared to chemical reactions. Again, these fission reactions release all these neutrons, so that with one target nucleus here, you'll break into a couple of smaller pieces here, and you still release all these neutrons that can then go on and hit these other additional target nuclei, which then release neutrons over here, and they can hit even more target nuclei. And it's just this whole thing that goes on and on, and what we call a chain reaction that will eventually just go until there's nothing left. So you start small, and then it goes and does it again, and does it again, and does it again, and does it again, and you just get all these things happening over and over again until everything's used up, and you get a ton of energy from this. While a fission reaction starts with one nucleus and uses a particle being launched out to split into 2 smaller pieces, a fusion reaction is the opposite. You start 2 lighter pieces and actually combine them to make one heavier, stable nucleus. So you're creating energy by combining atoms to make them form some other heavier element. So in this case, you could combine something like two hydrogen atoms and put them together to make a helium atom. And this is actually how we get energy in stars. This is happening all the time with hydrogen coming together and making helium. And this is actually how all these different elements formed when the Big Bang first occurred too. So this releases a lot more energy than a fission reaction. Fission releases a lot of energy compared to a normal chemical reaction, but fusion releases even 3 to 4 times more than a normal fission reaction. So it's just a lot of energy on top of what we normally would expect even. And in addition to this, you don't get radioactive waste, which is awesome. In nuclear power plants, we get a lot of power from fission reactions, but you also get radioactive waste, and you have to figure out what to do with these things. Fusion reaction is clean energy. So if we could figure out how to do this, it really would be incredible for our planet and just really a great source of energy that will be renewable forever, pretty much, because you could just take hydrogen from the air and combine to make helium gas. Could also solve the helium shortage. We spent a lot of time early in the year balancing chemical equations to show that what we start with is always what we're left with. You don't lose any mass, you don't gain any mass. Everything's always the same. We did that in lab work too. That's really not the case in nuclear reactions though. So there's always a little bit of mass turned directly into energy during nuclear reactions. It's not enough that we really measure it differently, and we don't really have to worry about that when we're looking at equations, but just we have to know it is there somewhere. It's small enough that we don't worry about it, but other people, like working scientists, would know about this stuff. And this small amount of the mass that gets turned directly into energy, so it's kind of lost in our reactions, is what's called a mass defect. Just means it's basically like the missing mass. So if you start with 10 grams of something, you may only get 9.9 or 9.8 grams of the product, because those small 0.1 or 0.2 grams would be turned directly into energy, and they don't show up in our reaction anymore. And this idea was actually predicted by Albert Einstein as E equals mc squared equation from way back when, that you've all probably heard of at some point. But it's just saying that some of that mass turns directly into energy, and we don't have to worry about it. So nothing to worry about, but it's there. We got to know this anyway. And just to again restate some things, nuclear reactions just have so much more energy release than any traditional chemical reaction. So it's always more energy involved than any of the other things we've seen this year. If I knew this when I was a kid, I may have made sure I mouthed off a lot more. What's the difference between natural and artificial transmutations? What they have in common is this word right here, the transmutations. So it's one element turning into a different element. Natural, you have one reactant. That's only because you have one thing that's on its own breaking down to something else, and that's going to be a spontaneous process. It doesn't need any outside assistance. It has an unnatural and unstable proton to neutron ratio, so it's going to break down on its own without any help from anybody else. In artificial, you have two reactants, because you're talking about stable reactants. It's not going to happen on its own. You have to shoot a neutron or a proton or an alpha particle or some smaller thing at what we call a target nucleus to make this otherwise non-spontaneous process happen. It would not happen on its own unless we did this. So it's non-spontaneous, and this usually releases neutrons also. So you might use a neutron to shoot that at the target nucleus, and it'll create something that's unstable, and usually releases a bunch of neutrons again to kind of go on and keep the whole thing working. We saw that chain reaction slide before. So what do fission and fusion have in common, and how are they different? Well, each of them are transmutations. So each of them, I'm just going to draw an arrow right down here. Each of them are one element, and another little arrow becoming another one. So you've got some element turning into a different element. In fission's case, you have one nucleus that's heavier, a heavier element, an unstable element, breaking into multiple smaller ones. So you have two lighter, I should actually write two lighter nuclei. And fusion is the opposite. Think of fusion, you're fusing things, you're putting them together. So it's two lighter nuclei combining to make one heavier nucleus. Simple difference.